All right, we're ready for some new slides. These are called pointers and memory, a very important topic, but unfortunately a historically difficult concept to understand for CSCI 40 students, so definitely pay some extra attention to these slides. And if you'd like to read something other than your book, there's a nice, helpful handout at this link, so take a look at that if you would like. It is nice and it explains pointers in a nice way. So let's get right on into it. What in the world am I about to talk about? What are pointers? That seems like a weird name for something. Well, let me at least teach you why you should learn about pointers. It's a way to get at the underlying memory usage of your program. It's a way to talk about memory itself, which we haven't really talked about. I've just told you that variables are boxes in memory somewhere. We haven't really talked about how or where or even why. So that is what pointers are all about. By learning how memory is arranged and allocated, we can write better programs. And also, you will, by the end of these slides, laugh at this comic. So that's another reason to learn about pointers too. Okay, so let's talk first about what memory looks like, because we haven't really gone there yet. I've just been drawing boxes, and that's a little too high level for what we're about to discuss. So memory, also called RAM, maybe you've heard of that too. So all the RAM in your machine, that is another word for memory. What does it have in it? How is it arranged is the question. So let's talk about this. So your computer's memory is really not a bunch of little boxes holding variables. It is a giant table, okay? A giant table holding things. It maps addresses. That's how you know where something is. And those addresses are usually 64-bit numbers, and it maps those addresses to bytes, 8-bit numbers. And that's what you're going to put inside of your memory. So here is my drawing of what memory looks like. It is just a table that for every address, there is a value associated with it. And that is memory in a nutshell. And so here's my big long table. Starts at address 0, and then it holds at every address, at every 64-bit address, it holds an 8-bit value, a single byte. So it holds like 42 at address 0, 1, 2, 3, so on and so forth. Alright, maybe it holds 43 here, maybe it holds 87 here, maybe it holds 88 here, not a problem. And yeah, it's just memory. This is what it looks like, and let's talk about why we need addresses in the first place, right? We want to hold stuff inside of our programs. We need places to hold those things, okay? So think of an address as the mailbox. It's the house. It is the thing that you can put an address on in real life, right? It's where you can go to find the thing you're looking for. So at address 3 lives the value 88. So I can remember address 3 to get here, okay? You can put data into an address, that's totally fine, or you can look up data that's there. That's essentially how variable accesses work. Like, I want to get 43, so I'm going to look up address 1 and see what's saved in there. Or I would like to increment the thing in address 2, make it 88. I would like to change the thing in address 3, 215 or whatever. Doesn't matter. So that is the kind of game you can play with memory, and that's deep down what variables really look like. It's just you're manipulating a value at a certain address, okay? So every variable or piece of data that you store in your program, everything you hold, has an address associated with it, because it's in memory somewhere, right? It has an address associated with where that data lives, and a better word than live is begin, because there are a lot of things in C++ that are longer than a single byte, and so we have the concept of a starting address. And I'll get into that in just a little bit. Okay, so that's memory. And let's talk about how we store a bunch of stuff. So for example, like I'm going to store an int in my program called x, holding 42. Ints are 4 bytes, right? They take up 32 bits. So how in the world are those going to get stored in memory if every single address maps to a single byte? That doesn't make a lot of sense, but there's a way. It's not too bad. So here's your addresses, here's your values. The idea is you have the concept of a starting address. Okay, ints take up 4 bytes in a row, and they're referenced by their starting address. So maybe this int x lives at address 16, we say, and so it takes up 4 addresses starting at 16. Okay, that's how it works. And so it's 4 bytes long over here. It's got room for 4 bytes, and this is the starting address. Okay, this will be where the integer x starts. That's all you really care about, where it starts, because then you know that because you have an int, it's going to last for 4 bytes from that starting address. And then somehow we're encoding the number 42 here in those 4 bytes. We'll talk about that later. Okay, so that's how you can store long integers. That totally works. And then that's really how you store everything, because remember that everything translates into numbers at the end of the day. Even for strings, you have your ASCII encoding, right? So doubles, for example, they're 8 bytes long, and they have some 8-byte representation that you can store in 8 bytes, given a starting address. That's fine. Same with strings. Strings are made up of a bunch of characters, and every individual character is actually a single byte, so that works out well. And so they're just contiguous in memory, a bunch of bytes in your string, okay? That's what those look like. And so this is really what's happening in memory when I draw boxes. It's living somewhere in this table. We're not sure where, but we know that an int takes up 4 contiguous bytes, for example. All right? So to talk at a better level about this, maybe a lower level or a higher level, depending on how you think about it, I want to teach you this thing called hexadecimal. It's hex for short, and it's just a different base. Okay, we've talked about base 2, that's binary. Hexadecimal is base 2 to the 4. It's base 16, okay? So instead of encoding a binary number with like 8 bytes, you can encode that same binary number in a very compact way using a bigger base, okay? So because it's base 16, that means you have 16 digits that you work with before you need another place, which is weird because we only have 10 in our normal number system. So that means we have the digits 0 through 9, and then we need another single digit to represent 10. So we're going to start with letters at that point. A is 10, B is 11. Just C by itself means 12 in hexadecimal. 13, 14, and then F is 15. F plus 1 is 1, 0, and that is 16. Okay? So you can count up to 15 before you need a second digit. Crazy. So that's hexadecimal. It's going to be very important because that's how memory is displayed to us. C++ likes to use hexadecimal, so that's why we're learning about it. And yeah, if you ever see like your computer print out or C++ print out a number that looks like this, it starts with 0x, that just is the terminal's way of saying that this number that follows that 0x is a hexadecimal number, because you can't use it like a subscript on the terminal. It's trying to say this number is a hexadecimal number. It should be interpreted as 1. Okay? So with that in mind, let's take a look at this. What is this number 3a in decimal? Okay? That is the goal. So let's try this out. What is this? So remember the way that you expand. So it's well, a times base 16 to the 0 plus 3 times 16 to the 1, okay? Which is equal to 16 times 3 plus, this is 1, a is 10, okay? Plus 10. And I did this ahead of time, and apparently the final answer is 58 in decimal. That's what that stands for, okay? So because it's a larger base, smaller looking numbers end up being bigger in decimal, okay? And so the nice thing about hexadecimal is because it's base 2 to the 4, you can kind of separate every binary number into 4 digits, and each group of 4 digits becomes a hex digit. I can prove that to you in office hours if you would like, but it's a very nice concept. That means that every number, every 8-bit number is 00 all the way to FF, because every single hex digit represents 4 bits. Okay, so 2 hex digits gives you 1 byte of information. And so it's very compact. You don't have to write 8 bits. You can just write 2 hex digits and you have represented a certain byte value. So that's nice to have, and that's why we use hex a lot. Okay, so with that, let me give you an example of like all this happening all over again, but let's talk about how memory is really working. Okay, so we're going to run those 3 lines of code. What normally happens, right, when I draw this, it's like, okay, X is a box in memory, it holds 42, Y is a box in memory, it holds 43, and Z is a new box in memory, also, it holds whatever Y held at that time, and it looks like Y holds 43. So that is what we have now, but we have new things to worry about, okay, or to understand. This is an old thing. When you make a variable, it creates a separate place in memory, because it's not a reference, right? So they're all separate boxes, which means they live in memory in different places. Another way of saying that is they have different memory addresses, okay? That's important. So maybe the address of X is 4, the address of Y is 8, and the address of Z is 12. It doesn't have to be that, but they could be. And actually, these 2 lines mean the same thing. They are equivalent. Isn't that interesting? Separate boxes means separate addresses. So we can translate this to our address value table, because that's what memory really looks like, in this way. So you got your memory, and then the starting address of X is 4. It takes up 4, 5, 6, and 7, all of those. And the value held, like X starts here, the value held in those 4 bytes is 42. And then you have 8, 9, 10, and 11 that belong to Y, and 12, 13, 14, and 15 that belong to Z. And you got more below. Okay, so that's Y, and that's Z taking up those next bytes. 43, 43. Okay, so that's really what's happening in memory. And so, really, a unique name for a variable is just its starting address. That's what the computer cares about. Humans, we like to use variable names like X and Y, but computers, all they need are addresses. Like, oh, this is an int that lives at address 4. This is an int that lives at starting address 8. Takes up 4 bytes, 4 addresses. So, yeah, that is ints in a nutshell, now that you know more about how they're really stored. So, with that in mind, I am going to give you a question that you already know the answer to. It's just a different form of what I've shown you before, just to wake you up. So pretend that it's your birthday, and I've made a birthday function for you. So here's int age equals 19, print it out, call birthday on age, which is supposed to increment whatever it was given, and then see out age again. What's going to happen? You tell me. So, if you remember, this is a normal int, so it's getting a copy, right? It's passed by value. So it's going to print 1919. It's not changing the original age variable. Yeah? One way that we know how to do that, to actually change it, is to pass it by reference. That's not happening here. So in the stack, it's getting int a as a separate place from int age. All right, so it's going to print 19 twice. Definitely try that if you don't believe me. And that is that. So yeah, we know how to fix this problem with references, but let me tell you right now that references are secretly using this concept called pointers, okay? It's doing the hard work for us. Oh shoot, I think I clicked too far ahead. I'm gonna get there in a second. Let's do this first. Let's talk about what went wrong, right? So this is the stack main calls birthday, but those were 2 separate places in memory, right? So we had age being set to 19 in main, and then we called birthday with age as an argument to the parameter a, and it is then going to make a stack frame for the birthday function being called and sets a to hold the value of age. But it's a different place in memory. It's got a different address. You see that? That's the key. And we can do a plus 1, or a equals a plus 1, and that will change a up here to be 20. Nope. I do not know why I cannot draw. There we go. That will change a to be 20, but that did nothing to the original age that we cared about changing, right? That is the story of why that's a problem. And now we're ready for this slide. I jumped the gun. So we totally know how to fix this with references. We just add a little ampersand here, and then A is another name for age. But secretly, references are using this concept called pointers. That's a lower level way of talking about memory. Okay, so let's learn how that really works, because pointers were the original thing. References are unique to C++. Pointers have been around as long as computers have been around. That's a very powerful, important concept that we have to learn about. Okay, and it has to do with memory and addresses. So let me introduce you slowly to this concept of pointers. Alright, so a pointer is a variable. It's another place in memory, it's a box, but the kinds of things that a pointer holds is different. A pointer is any variable that doesn't hold like a normal number or a string or something, it holds a memory address. Interesting. A pointer is a variable that holds a memory address, okay? That means it's a variable that holds the address of another variable, usually, right? Because that's the only other thing that we know lives in memory. So a pointer is a variable, and it is able to hold the address of another variable. And the reason it's called a pointer is because we say that pointers point to places. A pointer points to that variable that it's holding the address of. Okay? And don't worry, I'm going to give you a million examples, but I have to say some words first. So just hang in here with me, and we'll get to the examples soon. So here is how you declare a pointer. It's just a variable, so you give it a name just like any normal variable, and then you say, okay, if it's a pointer and it's supposed to hold the address of an integer, you say int star. Okay? It's always the type that you're pointing to, and then a star instead of like an ampersand. It's another type modifier. Okay? And again, the white space doesn't matter around the star. That's not a big deal, but a pointer is type specific. So if you want this pointer with this name to point to an integer variable, then it better be an int star as a type. If you want it to point to a double variable, it better be a double star as a type. Okay? So just keep that in mind, and now let's talk about how they work. So here is a declaration of a pointer to an integer. You kind of read it backwards, like for references. P is a pointer to an integer. Okay? And what it's going to do is make a place in memory called P. It's going to be set to garbage, as any other variable would be set to garbage. And P also has its own memory address, just like any other variable. It's just capable of holding other variables' addresses, which is cool. So if you're not sure what you want to point to yet, if you don't have another integer ready, then you can make P point to something other than complete garbage. A place that is nice and logical is called the null pointer. Okay? The null pointer is the number 0. Actually, in C++, you're never allowed to access the address 0 in memory. The 0 address is just off limits, and you're not allowed to access it because it is a nice default value for pointers that have nowhere to point to. Okay? So null pointer is equivalent to the number 0 in a sense, and it's a special unused address. Okay? That's a good place to do that, and or a good way to do that. And now let's actually use these things. Like, what can I put? How do I put an address of another int variable inside of P? Let me show that to you. So here is the setup. Let us make an int and a pointer to an int. Okay? So eventually we're going to have P point to the address of this other integer x. Okay? That is the goal. So what I would like to do is notice what's happening in memory. Like x and p are both variables, which means they both have addresses. P is a pointer to an integer. It is capable of holding the address of another integer. Hey, I have one. It's x. I would like to put this address in P. That's what I want to do. I want to put 100 right there. That's what I want. So the question is how now? Here's how you do it. So here is the secret. So what you do is you use the ampersand. I'm so sorry, the ampersand has already been introduced to you in a type. The ampersand outside of a type involves pointers, sadly. So the operator ampersand, when used outside of a type, is called the address of operator. Okay? It returns the address of the variable that you put right after it, okay? So this line, you read it as P gets to be the address of X, okay? Read this as, this is address of operator, and this is the thing you're taking the address of, you're finding the address of, and so this is address of X. That's how you read that line, okay? P equals the address of X. And that will set up this situation. P will then hold 100. It's a pointer, and so we like to draw little cute arrows saying that P is really pointing to this box, okay? That's how that works. So let's see here. I think let's start here. Let me start making a file and show you a little bit about what's going on here. So int x equals 5 apparently, int star p, right? Let me go through a lot of different steps here. So p is a pointer to an integer that's capable of holding the addresses of other int variables. Okay, so let's print just p right now. And then let's, well, let's start there. It looks like it is set to the special default value of 0 for us, but you cannot assume that, okay? So a better way of doing things is to, it might not actually print 0 if you run it on your end, on your own computer. The best way of doing this is to set p to null pointer, okay? That makes sure that it is holding a special unused address, okay? And so now it's definitely 0 if it wasn't before. And then we can have p hold the address of x, okay? We're using the address of operator. Okay, so now p holds whatever the address of the x variable is. And if I see out p again, here's what p holds. Now you see how it changed when I reran the program? Crazy, huh? So it doesn't start at 0. So, not always at least. And so here was what p was holding, the garbage that it was holding before. Here is what it holds when we set it to null pointer. And here is apparently the address of x. This right here, this fancy number, is the address of the x variable in our program. And we have a lot of memory in our computers. Every time we rerun the program, it gets loaded into a different place in memory. So now here is the address of the p, or sorry, it's the address of x, which is placed into p. We're printing p, okay? And so it's outputting this as a hexadecimal number. Isn't that nice? And you can tell it's 64 bits because every set of 2 is a single byte, right? So you have 8 bytes. That is the goal. 2, 3, 4, something like that. Okay, so that is what I wanted to say there, and I think we're ready to keep going. So I have placed the address of x in p right now. What good is that? P points to x. How could I use that idea? So here is how you use it. When you use the star outside of a type, here I am making p using it inside of a type, but if you use the star outside of a type on like the right hand side of an equality or in a cout statement, something like this, cout star p, what it does is it follows the pointer. It's called the dereference operator, okay? It follows the pointer that appears to the right of it. So like cout, the result of following p, okay? So see if you can think of, take a guess for what you think this code should print when I run it, given this state of memory and these values. Okay? What does cout star p mean? What does it mean to dereference p? What does it mean to follow a pointer? Let's see if our intuition is correct. Drum roll, please. That gives us 5. That follows p and doesn't give back like the address. It doesn't give 100 because that's just normal p. If you print p, it'll give you 100 back. So it doesn't print that. It doesn't print the address of P. You could use ampersand P to get that, but it follows P, goes to that box there, and gives the value back. That was held inside of that box. So star P is essentially another name for X at this point, because P is pointing to X. Yeah? That is the idea. And so this is like the original references. It's another name for the original variable. Isn't that cute? So yeah, that is dereferencing. That's following pointers to get at things, because P points to X, so let's follow it and get the value there. We have another way of accessing an existing place in memory. Okay? So yeah, more terms. This idea is called indirection, because we have like an indirect way of accessing X now with P. And yeah, what you do when you dereference a pointer, you get the value held at the thing you're pointing to, or the pointee. Okay? So it gives you the contents of that box in memory. That's quite nice. And because you have this ability, you can use these pointers. If you have a pointer pointing to something, they let you both access, like you're doing here, access a value pointed to, or modify it. Allows you to access and modify another variable indirectly. So here, if I have this state of memory, as we did before, X, and sorry, not Y, but P, and let's say their addresses were 100 and 104, so P was pointing to X, X held 5, and P was pointing to X because it held the address of it, so 100, and so we draw it like this. And so here's what happened. If you say star P equals 6, that is, okay, follow P to get to this box of memory and change it. Put 6 in there. So it's going to do this. That's equivalent to X equals 6. Does that make sense? Because of this setup, star P is equivalent to X from now on, until we change what P points to. Same with this. Star P equals star P plus 1. So go to that box of memory that P is pointing to, add 1 to the value, and also set that box to that incremented value. Okay, so that'll make it 7. So that's equivalent to X equals X plus 1. Okay, it's just star P is another way of talking about X now. It's an indirect way. Okay, so now here is another way of solving that birthday problem. You can use pointers. Instead of passing along the age normally, just the age by itself, you can pass along a pointer. If you pass along a pointer to an int, you can, through the pointer, modify the original value. So that's pretty sweet. This is going to work, and let me show you in the stack what's really going to happen here. Because we need to pass along a pointer to an integer now, instead of passing along the age itself, we'll pass along the address of the age. And so it'll set things up like this. So say that the age variable lives at address 100 in main. Once we call birthday, we pass along the address of age for the a variable now. It's the a pointer now. And this is what it holds. It holds the address 100, which then points through the stack frames down to main's age variable. And so indirectly, by using star a everywhere, we can change that age from 19 to 20. Isn't that cool? So that is much better than what we had before. So let me show you this. This is called, the original way that was copying was called call by value. The second way with references was called call by reference. This is either called call by address or call by pointer. Let me just pick one of those names for this. Okay, so let's see how much of this I can copy and paste successfully. I will be surprised if I can do it all. Yeah, it has weird characters when I paste it from PowerPoint, sadly. We will fix. I think it's happy. So yeah, this is called by address now. It's getting, we're passing on the address of A, and that was really going to change the thing and make it that 20. Okay, it's going to change the original age variable. Yay! Because we passed along a way to get there, an indirect way of getting there, into A. Okay? And so, secretly, when you use a reference, C++ is handling the pointer manipulation for you. It's putting the stars all over the place. That is secretly what references are doing for you. Okay, they're using pointers. And so I was kind of wrong to say that they don't take up any memory of their own, but they are just one box. They're just a box holding an address, which is much better than a giant vector, for example. Okay, so that is call by address, using pointers to do things for you. Okay, using those addresses of other things. So here's an example. Let us get some experience with pointers to pointers, because that's totally possible. Okay, so given this pointer diagram, for example, let's think of all the different ways that we could change the original variable, okay, where the original variable is x. So this is x right here. Let's just say that x is an int. It's a normal int. And these are the pointers that I have going along here. So I would like to be able to change this box in a bunch of different ways using indirection, using pointers and following them. Okay? So one way to change this box is, of course, to say the name x. Just be like x equals 6, please. That totally works. That'll change this box just fine. But I also have some pointers that can get me to x. So here's another one that is just like what we had before. P holds the address of x, and so if I say star p, I'm able to set that box. Okay? Does that make sense? Same with q. Q is another pointer that holds the address of x. So I can use it. And then you might not believe it, but you can have pointers to pointers. R is a pointer to q, which is itself a pointer to x. And so let me show you how to get to this box through R now, right? So if you say R, that's here. If you say star R, that gets you here, right? And that's the same as Q. How do I use Q to get to X? Well, I gotta star it once more. Star R equals 6. That's the fourth way to change X. So each of those pointers, it works just like that, okay? So that's fine. And also, if I give you this kind of diagram on a test, what do the types have to be for these variables? How would you have declared them? Assuming that x starts out being an int. What are the types of p, q, and r? So let's talk about this. This is important. So p is a pointer to an integer, right? Because x is an int. That means p better be an int star. Yes? That's how that must work. Same with q. Int star q, because q holds the address of an int variable. R holds the address of q, which is an int star. So I need another star. You see that? R is a, well, you can think of it this way. Read it kind of backwards. R is a pointer to an int star, right? I just put another int star there. So it's int star star r. That's how it must be declared. I hope that makes sense. Because q is an int star, and so r is a pointer to an int star. That's how you read that. And if you had another one, like z at, I don't know, some address, holding the address 250, it's the address of r, so it's pointing to r, that is now, z must be a, well, z must be a pointer to whatever type r is, a pointer to an int star star. So that's the kind of indirection you can have. That's int star 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 z. Okay? So, yeah, let me kind of show this to you, and we'll code it up. Okay? Let's go back to this file. I guess I already have p just fine. Let's have int star q equal the address of x as well, because that needs to happen. I need to get the address of x. That's 100. Put it into q. And then r needs to hold the address of q, right? So int star star r holds the address of q. Does that make sense? And then if I wanted z as well, int star 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 z holds the address of r. And that will make that diagram, okay? And so I can get to that original x in a bunch of different ways. See out, well, just x, or I could see out star p, star q, star star r, or star 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 z. Okay? Hopefully my drawings made enough sense. I guess I can have a new line for here. Oops. Yay, so a bunch of 5s. Okay? That's how it works. So that's how I can indirectly access that original x with a bunch of different pointers. Okay? Another thing that I want to just hint to you about is how you might come up with these types yourself, how you might understand them. Because eventually you have to give the address of x into p, right? So let's talk about the types involving the address of operator. So x, for example, is an int by itself, but when I say ampersand x, it gives me the address of x. X is already an int, so the type of this big expression, ampersand x, is int star, right? It gives the address of an int pointer. Does that make sense? So same for this. If I was to make a pointer to p, I would use an ampersand to get there, just like I made r equal to ampersand q, the address of q. So let's do this one, I guess, because we are setting r to it. Q by itself is an int star already. It's a pointer to an int. It holds the address of x. If I put an ampersand before q, the type of this whole thing is a pointer to whatever q was. So it's star, int star, right? Int star star, total. So pointer to an int. So that's what the ampersand does. It kind of adds on a star to the type. And that's what allows us to set these things in this way. Always adds on a star to the existing type of that variable you're taking the address of. Okay? So that is, I can imagine how complicated this might seem right now. Come back and study this, okay? This is a complicated topic, and examples are very useful. So that is what I want to say here for now. I think I just have a couple more things to say for this lecture. Let's talk first about segfaults. This is a type of error, a new type of error involving memory, okay? So let's talk about it. So when you write a program, of course, you have a bunch of RAM in your computer. You only have so much RAM, right? You can't try and make a giant vector that holds more ints than your RAM can hold, right? So your program only has so much memory assigned to it from your operating system. You don't even have access to everything because like Windows is running still, PowerPoint's running. It's got to use some of that memory for it. And so that's the first thing. And if you try to access memory that isn't yours, that the operating system did not give you, or if you try to access that special null address, that 0 address, that is not allowed to be accessed, then you get what's called a segmentation fault. And you might have seen this already when using like arrays. You get a segmentation fault, Segfault for short, and this is a runtime error. That's saying you try to access memory, it's not yours, sorry, can't do that. So yeah, let me show you an easy way to segfault. Int star p equals null pointer, and then see out the address of p. Nobody gets access to the null pointer's address, so this is not allowed, and so it will segfault. Boop. Oh, sorry, I need to compile the actual file that I just wrote. There it goes. So segmentation fault, core dumped, blah, blah, blah. That is a runtime error. You did not have access to the memory, the box that you get by following P. So we couldn't go there. Segmentation fault. Okay? That is a runtime error. And now you know. So if you try to access memory that's not yours, you're going to get that. Another way of accessing it very easily is to make like a pointer in star q and never initialize it, right? Because it's going to get a random address. Most likely that address does not belong to your program if you were to go and dereference it. In a very small case, this might actually work, but who knows? Okay, so also not allowed. Both of those are bad. So I guess I'll uncomment both. So that's a runtime error, a segmentation fault. It's a new kind of error involving memory. Now you know more about it. I think we're ready to talk about pointers versus references now. Like what's really the difference? What needs to be different when we think about it. Let me show you how to swap two variables. Okay, let's swap the values of two variables using references and then using pointers. Okay, swap by ref and adder.cpp. Okay, so here is, let's make two variables. Int x equals 42, int y equals 43, and let's make a swap by reference function that takes x and y, and hopefully it's going to swap them, right? It puts y into x and x into y. So let's make this one. That's totally fine. And this is what we know how to do already, right? So this is swap ref. It's going to take two integer references. It's a void function. Swap ref int ampersand, int ampersand. And just for fun, let's have these called a and b up here in the parameters. So swap by reference, it's just, okay, let's swap these things. The only thing that needs to change are these types here. We're getting those A and B by reference, so they are the same as what was passed, so we can actually modify them. So that will give us int temp equals A equals B equals temp. I'll swap them. Boop. And so now we get 43, 42, perfect. That's a normal thing that we know how to do. That's swap by reference. And so let me draw to you what's going on the stack there. We had main had x, and main had y, set to 42 and 43. And then we called swap ref, and my reference, my functions that take reference parameters I like to draw in green because they own weird things. Swap ref. Everything that swap ref owns, it looks like it has a temp, so it definitely needs temp up here. And it's going to set temp to be A. But what are A and B? Because they're references, they're a reference to X and to Y. They're new names for those existing boxes. So this is A and B inside of swap ref. Okay, hopefully that makes sense. And so I'm putting A into temp, so temp holds 42, and then I'm using that to swap things. So this becomes 43, this becomes 42. Okay, because I saved it into temp. And so that's what references allow you to do. Just a new name for an existing variable. And now let's do the same thing with pointers, okay? So swap PTR. If I want to swap by the addresses of these things, I need to pass along not x and y, but the addresses of x and y. Okay? That's what needs to happen. And that will allow us to get to x and y just indirectly this time by following a pointer. So let's change this around. Swap PTR. So this is int star A, int star B. These are pointers to ints now. So temp needs to be the value that's held in x right now. A is pointing to x, so we better say star A. There's a bunch of stars all over the place now. Star B, and then temp's still a normal int, so I don't have to put a star anywhere near temp. But that is how that's going to work. Okay, swap pointer. And so this will put it back to 42 and 43, because it swaps the 43 and 42. Okay, and now let's talk about how this is running, why it's doing what it does. Okay, so let's go back to blue. Main. Now x and y are 43 and 42, so let's draw that. And then I call swap by pointer. And something interesting here is swap pointer has three variables total inside of it, three local variables. The parameters are local variables again. These are just normal variables. Pointers are normal variables. They just happen to hold addresses of other places. So A and B, they do live up here. They hold the addresses of x and y. So maybe x's address is 100 and y's address is 104. When I call the function with the address of x and address of y, that puts into A the address of x, 100. That puts into B the address of y, 104. And so I have this kind of situation going on now. That's how I'm allowed to get to those original variables. Okay? And then temp exists as well. We say temp equals star A, so go here, get the value, put 43 into temp. And then we say star A equals star B, so star A, go here, set this thing to going here and getting this thing. Okay, so put 42 into X, or star A. And then finally star B equals temp, so go here, set this to whatever's in temp, 43. And that's why the swapping works. Okay, so please yell at me if you have any questions about this. This is a weird kind of new topic. Pointers are odd, but they are powerful. Okay, it allows us to talk about the addresses of our variables and indirectly access our variables using those addresses. Okay, so that is pointers versus references. Hopefully that was a good enough example for you. And then the final thing that I want to show you here in class today is what happens when you take pointers to classes. Okay, so this is what I'm talking about here. So like a string is a class, right? So if I make a string, I can make a pointer to a string. That's totally fine. Have it hold the address of X. I am not allowed to use the dot on a pointer, because think about what this is, right? I have S, the original string. It holds A, B, C, D. Maybe its address is 100. Then I make SP a pointer to S, which means it holds the address 100. This is just a number. You can't say dot size on a number. That makes no sense. So SP.size won't work. What you have to do is follow SP to get to S so that you can dereference it. Okay? So you have to say star SP, that gets you here, and then you can say dot size. I hope that makes sense. This is kind of ugly looking, and you're forced to use parentheses too because of precedence rules. People hated this idea, so instead of star SP in parentheses dot size, C++ people came up with the arrow. Actually, the C people came up with the arrow. So the arrow is the same as this thing. Instead of saying that, you can say SP arrow size, and it both dereferences and dots SP. Okay, that's what the arrow does. So that's quite nice. Those are two equivalent statements. That is the goal, because star SP gives you S back in a sentence. All right, so that is that. Let me just briefly show you all this, and that will be the slides for the day. Arrow operator. So let's have a string, and then a string pointer holds the address of S. So I need to be able to do this. Cout sp.size won't work. That won't even compile. I have to do it like this. Cout either star sp.size or sp arrow size. Those are equivalent. So those will both get at the original S string and do the size operation on it. That's the arrow operator for classes that have things that you want to take the dot of to get inside of. Okay, so that'll print 4, which is exactly what we want here. That is S's size. So that is the last little piece of syntax I wanted to show you. So that's the end of these slides for the day. The next thing that I want to talk about is because it is week 10, remember that you have a test coming up. So I promised you a second midterm in week 12, so we're 2 weeks away. And so let's talk about that. I have a midterm info page that I'll release and an extra credit assignment page that I will also release. So here it is, midterm 2 info. Let's talk about it. The midterm 2 will be available for those same days that I made midterm 1 available. It's 5:30 p.m. on March 30th. That's week 12 Wednesday to 8:30 p.m. on March 31st. That is the Thursday. Okay, so Wednesday and Thursday, you have to take the test sometime in that range. And I will be on Zoom, again, to answer any questions if you choose to take it on during that time. So I'll be on Zoom in my CSCI 40 class from this time on the Wednesday. So that is when it's going to take place. And here are the things that I'm going to test you on. Okay, lectures through week 11, SciBook readings and SciLabs from chapters 5 through 7, and labs 4 through 6. So here are the topics that I want to test you on. It was hard for me to do this, but I think that I'm not going to test you on pointers. I think classes will be the last major topic. If I do test you on pointers, it will be very simple questions. You have my promise on that. Okay? So with that in mind, that is what your midterm is going to be about. And sorry, this looks like this. Let me fix that a little bit. It's going to have the same style of questions as before, so prepare to write code and to paste code, and it's got the same format. Okay? So here are some sample questions from last semester. We didn't have a million holidays last semester, so I did test the students on pointers during the second midterm. So you can just disregard any questions that are not about these topics. Okay, so that's what you can expect. That's kind of what the test will look like. And that's all I wanted to say there. In addition, because it's a new test, there's a new extra credit opportunity for you. So this is the same as midterm 1. Make a midterm 2 review video, please, if you would like up to 2.5% extra credit. Same exact rules, so I don't think I need to re-explain. But yeah, just make a nice video going over stuff relevant to the topics that will appear on the test. Give a little mini lecture, and your peers will love you forever. Okay, so that is your extra credit assignment, and that is your midterm. And I think that's everything that I wanted to talk about. So please yell at me if you have any questions about anything, and I will see you next week.